Welcome to Chapter 10, the first screencast. This is going to deal with liquids, solids, and phase changes. In the previous chapter, we looked at gases, and in gases the molecules are very far apart from each other, and the attractions between the molecules are very small, small enough that we can essentially say they're negligible or not significant, certainly for an ideal gas at least. But if we deal with liquids or solids, now the molecules are close to each other and the attractions are significant. We have to take them into consideration. So as we continue studying the three phases of matter, we're going to start looking now at the forces that act between molecules. So here's a molecule, here's another molecule. We're going to be looking at the force between this molecule and the nearby molecule, not chemical reactions, not bond breaking, but forces between molecules. It turns out that lots of chemical properties, ranging from pretty simple things like melting points and boiling points and what sorts of substances dissolve in other sorts of substances, on up to pretty complicated things like the structure of protein, how DNA functions to transfer genetic information, and a whole host of other things can be understood by looking at intermolecular forces. So we're going to spend some time now looking at intermolecular forces, and we're going to abbreviate them as IMF. So when the mission is impossible or the forces are intermolecular, we'll be using IMF as our abbreviation. So some measures of strength of attraction between the particles of a compound. Let's say the molecules making up a compound. Well, there's lots of things that are rough measures of how strongly the particles attract each other, such as the boiling or melting temperatures. Things that have high boiling points will have strong attractions between their molecules. Things that have high melting points will have strong attractions between their molecules. If the boiling points or melting points are low, that's indicative of not as strong attractions between molecules. Similarly, enthalpy of fusion, which is melting, or enthalpy of vaporization, which is the phase change from liquid to gas, specific heat, heat capacity, solubility, surface tension, viscosity, and others are all measures of strength of attraction between particles of a compound, and we'll deal with most of these during this unit at some point. Now let's start by considering two substances that are both ionic, sodium chloride and magnesium oxide, and let's compare their melting points and explain why they differ. And note, these are not actually intermolecular forces, but this is a way to kind of get at some of the concepts by way of introduction. So sodium chloride is made up of sodium ions and chloride ions. They attract each other. And note that their attraction is an ionic bond between a positive one charged sodium ion and a negative one charged chloride ion. And that's a pretty strong attraction, and you have to heat sodium chloride up to 801 degrees Celsius before it melts. Now, how about magnesium oxide? You might think about this for a minute and see if you can predict what kind of melting point this would have, magnesium oxide would have, compared to sodium chloride. And if you think about it, you'll note that magnesium oxide also has an ionic bond, but its bond is between a positive 2 charged magnesium ion and a negative 2 charged oxide ion. And as you would probably predict, the attraction between +2 and -2 is quite a bit stronger than that between +1 and -1. And the melting point is, as a consequence, quite a bit higher, 2,852 degrees Celsius to melt magnesium oxide. We've doubled the charge on both particles, so it's something like 4 times the amount of energy needed, but of course there's different sizes of molecules as well, so it's not exactly that, but it's a lot stronger attraction, a lot higher melting point. So here's our generalization. If we have larger charges in ionic compounds, the attractions will be stronger and the melting points will be higher. Now we're going to use this kind of reasoning to deal with intermolecular forces in non-ionic compounds, but in covalent molecular compounds. Okay, so we will now move on to some molecular or covalent compounds, and we will compare the boiling points of two substances, F2 and HCl, and explain why they differ in terms of intermolecular attractions. So fluorine, F2, is made up of two fluorine atoms covalently bonded. HCl, hydrogen chloride, is made up of a hydrogen covalently bonded with chlorine. And we note that fluorine is a very electronegative element, as is chlorine, not quite as much though. But the two fluorines are bonded together, whereas chlorine is bonded to a hydrogen, which is less electronegative. So what we have is a fluorine molecule is nonpolar, perfect sharing of electrons between the two atoms. The molar mass of fluorine is 38 grams per mole, and its boiling point is pretty low, negative 188 degrees Celsius. Now what would we predict for HCl? Well, HCl is polar. There's a dipole from the hydrogen to the chlorine, unequal sharing of electrons. Its molar mass is about 36.5 grams per mole, reasonably similar to that of fluorine. And would we expect its boiling point, therefore, to be similar or lower or higher, and why? Well, polar molecules have positive ends and negative ends that can attract each other, and it turns out that that attraction makes the boiling point of HCl quite a bit higher than that for F2, and in fact it's negative 85 degrees Celsius. Now note, that's not a very high boiling point, but it's about 100 degrees Celsius higher than that for fluorine. So if we compare fluorine to HCl, what we note is fluorine has a nonpolar molecule and another nonpolar molecule, and the attraction between those two is not very strong. But HCl has a polar molecule, and if it's near another polar molecule, the negative end on this molecule attracts the more positive end on a nearby molecule, and that attraction is quite a bit stronger than for F2, and as a consequence, HCl has a higher boiling point. So, as a summary, HCl has a higher boiling point than F2 because it has an attraction between a dipole on one molecule and a dipole on another molecule, and rather imaginatively, we call this a dipole-dipole attraction. So as a generalization from these molecules to others, the more polar a molecule we have, the stronger its attractions. Because it has bigger dipoles, it'll have stronger attractions between the dipoles, and the higher we would expect its boiling point to be. And the same argument would follow also for melting point and other measures of strength of intermolecular attraction. So dipole-dipole forces are the first intermolecular force that we have been introduced to. Now, the next example, let's compare fluorine to chlorine to bromine, and note that these molecules are all covalently bonded, perfectly nonpolar, exact sharing of electrons between the two F atoms, between the two Cl atoms, and between the two Br atoms, respectively. And the boiling points, while fluorine we've already seen, negative 188 degrees Celsius. Now chlorine, Cl2, is a bigger molecule, and you might think about whether you think that will mean that the boiling point of chlorine is higher or lower or about the same compared to fluorine. And it turns out it's a fair amount higher. And now we seem to have a bit of a trend, perhaps. Let's check with bromine. Yep, that one's even higher yet. So we definitely have a trend. As the molecule gets bigger, it looks like the boiling points go up a fair amount. So why would that be? And here the boiling points are converted to Kelvin temperatures, 85 Kelvin for fluorine, 239 Kelvin for chlorine, and 332 Kelvin for bromine. Now, here are their molar masses, 38 grams per mole, 71 grams per mole, and 160 grams per mole. So note there doesn't seem to be like a linear relationship or anything like that, but as the molar mass goes up, the size of the molecule goes up, the boiling point goes up as well. And what the reason is for this is if we looked at a fluorine molecule and represent its electrons by dots, at any given instant, fluorine has 18 total electrons, but at any given instant, it might not have 9 electrons associated with one atom and 9 electrons in the other. In other words, it might not have an equal or symmetric electron distribution. And if it has an electron distribution as is shown here, which is a little bit exaggerated, but at the moment, there's more electrons on the right-hand atom than on the left. That means that the right-hand atom is a little bit negatively charged by comparison to the left-hand atom, and that's a dipole. Now note, this is not going to be a permanent dipole, it's just a dipole that appears briefly, so we call it an instantaneous dipole. But the other atom nearby, fluorine, can also have an instantaneous dipole, and in fact, one instantaneous dipole can induce a dipole in a nearby atom, and we now have an attraction between the positive end of one molecule and the negative of another. And so even nonpolar molecules have attractions due to these instantaneous dipoles. They're also called induced dipoles, and these forces are also known as London forces or London dispersion forces or just dispersion forces. All terms are used. So our second type of intermolecular force is called London dispersion forces. It's an attraction between temporary or instantaneous dipoles in molecules, and all molecules have these, whether they're polar or nonpolar. And the generalization here is that larger molecules are what is said to be more polarizable, and therefore they have larger attractions between their molecules or larger London dispersion forces. And just a little more about what polarizable means. A larger molecule has more electrons, and it's a bigger electron cloud, and because of that, its electrons are a little more easily distorted than in a smaller, more compact molecule. So Cl2 would be more polarizable than F2 because it's larger and its electrons could be a little more asymmetric at any given time. And then bromine, even larger, another electron shell for each atom, and that's even more polarizable because its electrons can be even more distorted than in the smaller molecules. So as a generalization, larger molecular compounds have stronger instantaneous dipole attractions, and we can conclude that, of course, size does matter. And here we're talking, of course, about strength of attraction between instantaneous dipoles. Larger molecules have stronger attractions, and if size didn't matter, well, then King Kong would just have been another monkey.